to the movement of the wave.
Correct. So transverse wave is when, and we're just gonna, this is like what, the 5th time we've been over this, so we're just gonna write it very short and sweet. Particles are perpendicular. Okay?
So,
It's a nice, short, easy to remember phrase. Charlie, is that you with the question?
Yes.
Yes.
Are we going over last week's Bellringer?
Yes, this is last week's Bellringer on transverse waves as a review of wave parts and how we utilize them. On newtongrade5.com on our website, I have listed what the Bellringer for this week is, which should be wave behavior, because I think you have 2 again this week. So it would be wave behavior. Okay. All right, what's a crest? Who has a definition for crest?
I do.
You go, Casey. I don't know who I is.
A crest would be like the highest point of a wave.
Yeah. Now, I'm going to call it a wave form. I'm going to call it a wave form because obviously when we graph it out, we're just kind of graphing the movement of the particles, and we call that a waveform.
Mister,
Yes.
for the longitudinal wave Bellringer, are we supposed to save that, or can we like throw it away?
You can throw it away. You can throw it away. It's useful to you, but we're not going to go over it. Because most of the time when you look at waveforms, when you look at graphs of waves, you're going to be looking at transverse waves because they're the easiest one to spot all of the parts in, obviously.
So we don't need it?
Nope.
Okay.
Nope. Reagan, you have your hand up for a question, or do you want to answer trough?
For a question.
Yeah, what's
Are
up?
we just doing the Bellringer today, or are we doing notes too?
The Bellringer is our notes.
Oh, okay.
So yes. All right, what is a trough?
I know.
Nathan. He typed in the chat, if you're not looking, he said the bottom of a wave, and he is correct. I'm going to put lowest point of a waveform just to stay consistent with what we said what the crest is, because we know that the trough is just the opposite of the crest. So it's the bottom of the wave or the lowest point of a waveform. Okay. Allison, do you want to tell us what amplitude is, or do you have a question?
I want to tell you what amplitude is.
All right, go for it. What is amplitude?
Amplitude is the height of the wave?
Yeah, so this is the height. So we have the highest point, which means it's the furthest away from the equilibrium it can get, but we also have the measure of that. So this is the maximum displacement from the equilibrium. It's the farthest away any one particle will get from that rest position. It's a measure of the amount of energy in the wave. It's the measure of the amount of energy. Okay, and then we have wavelength. I know I'm moving kind of fast, but that's okay, because we're gonna take a break after we go through these so that everybody can have it written down. Gracie, what's the wavelength?
The wavelength is the height of one wave.
That is an excellent guess, although it is incorrect. So we're not gonna call it the height. We're not going to call it the height, because when we look at the kind of the tallness of a wave, that's more a measure of amplitude. Instead, we're kind of looking for the what? Bailey, what are we looking for here?
The length.
Yeah, so Gracie, height, we're thinking more up and down. Length, we're thinking more left and right. Truly, not too huge of a difference, but instead, the wavelength here is the length. So we're going to say the measure from crest to crest. That's actually what we're going to write down here. Because if I start at a crest and end at a crest, I have one complete crest and one complete trough. And that tells me exactly how long the wave is. Okay? So length from crest to crest. Or length of one complete crest and one complete trough, or length from trough to trough. We've measured wavelength a couple of different times here, but what the easiest points to find on a wave is the crests, especially in a transverse wave. Emily, do you have a question?
So it could be one complete crest and one complete trough.
Correct. It's the length of one complete crest and one complete trough, or it's the length from crest to crest, or the length from trough to trough. All of those, as long as you have a complete crest and a complete trough, is a length of a wave, because that's one complete wave cycle. We're going to say wave a lot.
Miss Sarah,
Yes?
can I answer frequency?
Actually, I was going to ask Susan, who's had her hand up, if she had a question or wanted to answer frequency.
I want to answer frequency, and isn't it the number of wavelengths per second?
It is. It is. Number of wavelengths per second. Okay, we're going to go ahead and make sure that we have all of this written down before moving on to part B, because part B is asking us to kind of dissect these two waves and consider the three measurements of these waves. And that can be a bit tricky. So we're looking at wave A, and then we're looking at wave B to figure out how are they similar in amplitude? How are they different? What about wavelength? What about frequency?
Are we supposed to draw that?
No, this is on the Bellringer. So what we're going to talk about before we move on to our notes is these two waves. And I've just pulled this up so I can draw and we can talk. Okay? Because the first thing that we kind of have to figure out here, the first thing it asks us to do is compare and contrast amplitude. And you all can see what I'm writing, yes? Okay.
Yes.
Perfect. So,
Are we supposed to write this down?
I'm going to write it down in my science notebook, and at that point, you can write it down in your science notebook.
So you'll show us what you're writing when
Absolutely.
you're done with this.
Absolutely.
Okay.
Yeah. Have no fear. Okay. So, obviously, amplitude is the measure from the equilibrium to the maximum displacement, which is either going to be the crest or the trough. So what we're looking at here for amplitude is that line. And that's for wave A. Amplitude here is our equilibrium to our crest or trough. Okay, And so our amplitude is there. So if we're going to compare and contrast these, we basically just need to say, do they have a similar amplitude or a different amplitude? What do you think? Looking at this picture, are they the same or are they different?
Different.
Yeah. Okay.
Very, very different. Because
Okay.
one has like is bigger than the other. Because this one is just to like
Use names, please. Not this one and that one. Wave A or wave B.
Put some of it on your finger, then wipe it on your lip. So like wave B, wave A is bigger, has like the amplitude is bigger than wave B because if you don't see, because they're farther apart on wave A, and on wave B they're closer together.
Okay. I see a lot of people mentioning that the crests are farther apart. So like this crest is a lot farther apart than that trough, than this crest and that trough, right? This is a really short compared to this. That is not a measure of amplitude. Amplitude is from the equilibrium. So do these two equilibriums line up? Yes or no?
Yes, they very much do.
Okay, yes, the equilibriums very much line up. Now this dotted line at the top here, this represents that maximum displacement. So do these line up?
Yeah.
Yes, they do. So if the distance between my maximum displacement and my rest position, if that is the same from this wave, from wave A to wave B, do they have a similar amplitude or a different amplitude?
Similar.
Put an S in the chat if you think they're the same. Put a D in the chat if you think that they are different. Yeah, so these actually are going to have a similar amplitude because their rests, similar, yep. Their rest positions are lining up and their maximum displacement is lining up, okay? So we will call that similar. And then of course we haven't written this down in the science notebook yet, but we will, okay? Next we have to talk about, that's an eraser, wavelength. So looking at wavelength, that is one complete crest and one complete trough, okay? So let's see, if this is meters, this one has a wavelength of 4 meters. Does everybody see that?
Mm-hmm.
This one is going to be one complete crest and one complete trough. I know it's not perfect. But again, if this is in meters, then this one has a wavelength of 1 meter. Are these similar or different? And S or D in the chat, similar or different? Yeah. Yeah, these are different. These are different. And when you guys were looking at your amplitude and you were like, whoa, that crest is really far from that trough, you guys were investigating wavelength. You were not investigating amplitude. It gets really easy to mix those two up or to think that you're looking at one thing, but you're really looking at another. So it's really important to keep track That's why I like to color code, because it helps me keep track. What exactly am I talking about? So for this last one, we're talking about frequency. Okay? Now, because we're talking about frequency, these boxes can no longer represent meters. Instead, these boxes are going to represent 1/4 of a second. Okay? So now, let's go with red. So
Okay,
now,
that makes sense.
yeah, because we can either measure frequency or wavelength, but not both. So now we're going to call this 1 second. So this would also be 1 second. Let's just straighten this back. Okay, so 1 second versus 1 second. So now we have to count those wave cycles per second. What are the wave how many wave cycles are here for wave A? That's 1 complete crest and 1 complete trough. Put it in the chat. How many? Yeah, I'm seeing lots of 1s there. So I've got this crest. So there's a half a wave. That, woo, went crazy there. That trough, there's another half a wave. So the frequency for this guy is 1. Okay. What about wave B? What's our frequency for B? What's our frequency for B? Seeing lots of 4s, lots of 4s. So I'm gonna count 1, 2, 3, 4 crests. Got 1, 2, 3, 4 troughs. This does end at the equilibrium. This one does begin at the equilibrium. So yes, this one is 4. So is their frequency similar or different? Yeah. Absolutely. Absolutely. All right. So coming back to our science notebook here, we're looking at that amplitude, that wavelength, and that frequency. Our amplitude was similar. Our wavelength was different. And our frequency was different. Now, if you want to be thorough in here, you know, wave A was equal to, 4 meters, sorry. 4 meters, I had those backwards. And wave B was equal to 1 meter. And then, of course, this one, wave A had a frequency of 1 versus wave B, which had a frequency of 4. If you want to be thorough. No, Charlie, it's not over yet. We still have part C. We still have part C to talk about.
Can you zoom out, please?
It just says amplitude and frequency, but yes. Okay, now part C. This one was actually surprisingly easy for being a part C question. We needed to draw a picture of a wave with an amplitude of 2 meters and a frequency of 0.5 second. Okay? So looking at our waveform graph, okay, obviously this is 0. You can call this 1 and this one's 2. So then this would be -1. This would be -2. Because I'm below 0 there. Now I'm redrawing this in my science notebook. You, of course, have the piece of paper, if you so choose to use that instead. This was our time in seconds. This was 1, this is 2, 3, 4, and then I think our graph went to 6, but we need 0.5 second. We need 0.5 second. So, how to do this? We need to indicate where our amplitude needs to go, and our amplitude needs to be +2. So, my amplitude is going to have to come up at least this high. It's going to have to be at least that high. If it's going to be at least that high, how low does it need to get? Does it need to go to -1 or -2? How low does it need to get? Yes, Blake. Yes, it needs to go to -2. Good job, Michaela. It has to come down to -2 because we know it's the opposite. We know it's the opposite, so it has to go to at least -2. Now for the important part. If it has to be a 0.5 second long, if the frequency has to be 0.5 second, how big do we need to make the wavelength?
Miss Sarah.
Yes.
So what I did is for like
Casey,
I
knock
did
it off or I'll
like
cut your video feed.
what?
I was talking to Casey. What's up, Charlie? What did you do? How did you solve this problem?
So what I did was so it said with 2 meters. So I did like 2 of the like loop type things on top, and then I made it all the way to 5 on the bottom because it'd be 0.5 seconds. So would that be right?
So, remember that our frequency is the number of wavelengths in 1 second. Okay? Number of wavelengths in 1 second. So here's my 1 second. Here's my 1 second. How am I going to make my frequency 0.5 second?
So would you, so there's, it's 1 second there. So like, would you go between the 0 and the 1?
So if I put one complete wavelength and if I can put one complete wavelength, so one complete crest and one complete trough in here, that gives me a frequency of what? 1. I need a frequency of 1/2. So if I put only half of the wave in 1 second, which means I go all the way up, down, crossover here, that's my crossover at 1 second, down to my -2 and back up. Now I have one complete wavelength across 2 seconds. What is 1/2?
1/2.
1/2. Is that what we needed?
Yes.
Yes. I have one wavelength over 2 seconds. One wavelength happening within 2 seconds. One wavelength, 2 seconds.
That makes sense.
Does it make sense, or are you just saying that to make me feel better?
No, that makes sense now.
She's probably doing both.
Does it make sense to you, Zeppelin?
Yes, it makes perfect sense.
What about you, Oakley? Does that make sense to you? Yep. How you feeling, Chase? Does it make sense to you? All right. All right, if this makes sense to you, you may leave. If this